Hello, I'm Professor Richard Tamboro, Daytona State College School of Mathematics. I'm demonstrating the traditional hypothesis testing technique for testing a claim for proportional data. Proportional data is any data that can be a percent or a proportion, and for those cases we use a test statistic with a population proportion and a sample proportion. Okay, let's take a look at our problem. You'll find these are very similar to t-test and sigma known and sigma unknown, sigma known being the z, unknown being the t. Proportion is typically your third type of hypothesis test. Okay, in this case, a proportion of people with a bachelor's degree, this data is from the US, it's real, is 0.25. So about 1 out of 4 people has a bachelor's degree. There's really no better way to represent this data than a proportion. So that's why it's represented that way. Now the population proportion, which is secret code for the population mean when it's a proportion, it's always in the test the claim statement. So that's 0.25. Okay, now it says the degree is equal to 0.25. It doesn't have to say equal to. If you just see is, if you've learned from your algebra classes, is another word for equal sign. This is a two-tail hypothesis test. Anytime you have equal or not equal, different, the same as, that's a two-tail. You could even go so far as to say if you don't see an inequality explicitly as part of your test the claim statement, or even an implication, if there's no inequality, it's a two-tail hypothesis test. With a two-tail hypothesis test, that means when we make our graph, we have a rejection region on the left and the right. Okay, so for this case, equal to, that's the unbiased, it's always equal to. Not equal to, that's the alternative hypothesis. So the alternative hypothesis is, in this case, a translation from the test the claim statement. Okay, next we can get moving towards our graph. We have a level of significance, which is alpha, that's 0.20. Because it's a two-tail hypothesis test, we take the 0.20 and split it in half. 0.10 on the left, 0.10 on the right. When we go to our table or wherever you might be finding your critical value, let's see, I think this is, 282. Let's write that down on our list. I suggest you make a list. It's very much to your advantage to have an organized layout for your data. So when you pull numbers and manipulate them, you have a nice list instead of reading through a paragraph. Okay, so we have a critical value of plus minus 1282, negative on the left, positive on the right. That is the critical values. Okay, two-tail always has two critical values, left and right. Okay, we're all set to calculate the test statistic, so let's go to that. I'm going to first find my p-cap. I can't just jump into the formula yet. I need p-cap. P was given. Q I'll need also. Q is the complement of P. 1 minus 0.25 is 0.75. These two numbers always add up to 1. Okay, we had 55 households sampled, or 55 people sampled. 18 have or had a bachelor's degree. So of the 55 sampled, 18 have a bachelor's degree. If you divide 18 by 55, that's x over n. That gives us p-cap. So in this case, p-cap is 0.327. Okay, so now I have everything I need for the formula. N, PQ, p-cap. Okay, so let's go to the formula. Be careful with the formula because you have to get the parentheses, everything in the right spot. Okay, so let's see. P cap minus P divided by radical PQ divided by N, all under a single radical, parenthesis, front and back. Okay, let's see. That gives us a result of positive 319. Let's see. We'll just put that down here. Again, I like to have a list. Okay, positive 319. Now, we could tell that this result would be positive because P cap is bigger than P. When you see P cap is bigger than P, your test statistic will be positive. If P cap is smaller than P, your test statistic will be negative. You may want to make a note if you're working a problem out, you're not sure, you can see if you can have an error that way. It's a way to check yourself. Okay, our test statistic. Now this one is a close call. 1319, and I'm at 1282, the critical value. So it's barely in the rejection region. However, it's in the rejection region. If that's in the rejection region, you reject the null hypothesis. If I had a test statistic of 1283, I'd be in the rejection region. I'm rejecting. In the real world of statistics, when we have a close call like that, there are some adjustments we can make as far as an elementary stat course. If you end up in the rejection region, no matter by what margin, you go with it. If you don't quite make it to it, you go with fail to reject. So don't try to make a judgment call. If you get to a higher order stat class, then you have a chance to do things like adjust your alpha and maybe look at indeterminate cases or whatever might happen. But for right now, even though it's a close call, you're in the rejection region, you reject. Don't worry about it being a close call. Now, because it's a close call, this is a case where my possibility of error type is 1, because when you reject, error type 1. Fail to reject, error type 2. We rejected error type 1. Now, this is a possibility of an error type 1, and that means that we're rejecting the null. Maybe we're wrong. Maybe we should not be rejecting. Maybe it should be fail to reject. If we reject the null, the implication is that the null is true, even though we can never prove a null hypothesis to be true or false, it's being supported. Now, because it's such a close call, there's a chance, a real chance of having an error type in this case. Now, in, say, a higher order stat class, you would calculate the alpha and beta analysis, and you would actually put a probability on your error type. So in a complete analysis, the statistician always estimates the probability that they have an error type. If you have a conclusion that has a 50% chance of having an error type 1, you've got to do something about that. Okay, you won't have those troubles in elementary stats, but if you're thinking of taking another stat class, those are the kinds of decisions you'll get to partake in, and they're very interesting. Okay, so we're about done. We just need to put a meaning on this. So we rejected the null. Our test statistic fell in the rejection region, not by a lot, but it's in there. We reject the null. We have a possible error type 1. Okay, so there is sufficient evidence to reject the claim that the proportion of people with a bachelor's degree in the US is equal to 0.25. So we're rejecting this claim. Thank you very much.